Okay, good evening, everybody.
Good evening, Professor.
And welcome to another session of organic chemistry. For today's session, we are going to finish up on chapter 7, which is concerned with the chemistry of alkenes. And then we are going to proceed to chapter 8, which is also concerned with the chemistry of alkenes. Okay, one announcement before we start. Don't forget that the next class exam is next Tuesday. That is October 22nd. And because of that, we are going to have an online review session on Sunday at 8 p.m. for those of you who can join us. That will be Sunday, 8 p.m., October 20. Okay? So when we finish that session, I will post the recordings in Blackboard and in YouTube. Okay? So that will be Sunday, this coming Sunday at 8 p.m. I will remind you again on Thursday. And for that review session, we are going to use the material from the fall 2012 second exam for that review session. Okay, so let us finish up on chapter 7. When we left on Thursday, we were discussing electrophilic addition reaction to alkenes. So what I want to do today is to finish up on this discussion, discussing carbocation rearrangement, and also to refresh your memory on Markovnikov rule. Okay, so we have electrophilic addition reactions of alkenes. If you take a look at this molecule here, with a carbon-carbon double bond, we told you earlier that the pi electron on the carbon-carbon double bond could be considered a nucleophile. In other words, it is rich in electron, and as such, it is available to attack a positively charged species, and that positively charged species we refer to as electrophile. It could be this hydrogen here, which is developing a positive character to it because of the polarity between hydrogen and bromine in the hydrogen-bromine bond. Okay, so what do we have here? We have this pi electron, the two electrons here. They will be moving to attack this proton here, to grab this proton. So let me go to a new page. I want to write it out for you, because this is a very important concept. Electrophilic addition to alkenes. So we have a carbon-carbon double bond. Keep in mind, our focus is on this carbon-carbon double bond right here, right here. The rest of the molecule is not, we are not concerned with the rest of the molecule at this point. Our focus is on this carbon-carbon double bond. Then supposing we now have hydrogen bromide. So what do we have? We have the pi electron here, which is 2 electrons. We move to grab, what I say grab, this hydrogen here. And in so doing, we are going to break the hydrogen-bromine bond. So we have this. Keep in mind right here we have hydrogen here also. So now we have this. The hydrogen that was there before is still here. As a matter of fact, let me change the color of this hydrogen bromide so we know the difference of the two hydrogens. Let me use blue here. Okay, so now this hydrogen was there before, is still here. So now we have this hydrogen now has been added to this carbon right here. And then what is going to happen to this carbon right here? Since we remove the 2 pi electrons, yes, becomes a positively charged carbon, right? Very good. So this becomes what we call a carbocation. In this case, this is a tertiary carbocation. That is a tertiary carbocation. And also, we know that we also form a bromide ion, which is here somewhere. Now the bromide is now negatively charged. Keep in mind that we broke the hydrogen-bromine bond heterolytically. We broke the hydrogen-bromine bond heterolytically, meaning that the bonding electrons, the 2 bonding electrons goes to the bromine atom. So we now form the bromide. So at this point, what do we now have? The bromide now will be acting as a nucleophile. This bromide now will act as a nucleophile. Come in here, these 2 electrons. Keep in mind, anytime you draw an arrow, what that arrow is telling us is that 2 electrons are moving. Okay? So now these 2 electrons now are moving from bromine to attack this carbon. So we are now going to form a bromine carbon bond. Bromine is here. Hydrogen is here. And the initial hydrogen is also still here. Now what I've given you here is what we call the reaction mechanism. In a reaction mechanism, what we show you the step-by-step, the details of how the reaction actually occurs, starting from going from the starting material to the final product. Now, if you look at this reaction here, the net process of this reaction is the addition of hydrogen and bromine across the carbon-carbon double bond. Hydrogen and bromine across the carbon-carbon double bond. Yes, net process, yes. Okay? Or in other words, what did I say, the outcome, the reaction outcome, or the product of this reaction. This is the product right here. In other words, the product of this reaction is that in which we have added hydrogen and bromine across this carbon-carbon double bond, such that the original sp2 carbon, this sp2 carbon here, this sp2 carbon here, now they are now sp3 carbon atoms. Okay? You also notice in this reaction, the hydrogen goes to this carbon, and the bromine goes to this carbon. So therefore, if you recall, this is what we call a Markovnikov addition reaction. Markovnikov addition reaction. And what is a Markovnikov addition reaction? This is very important, so I'm going to write it down for you in a slightly different language. Anytime, Markovnikov reaction is anytime you add an electrophile and a nucleophile across a carbon-carbon double bond, the electrophile will be attached to the carbon that contains more hydrogen. The electrophile will be attached to the carbon that contains more hydrogen. Okay. In this case, if you look at this here, the hydrogen is acting as your electrophile. The electrophile is the positively charged species, or any species that can develop a positive character to it. So the hydrogen goes to here, because if you look at these two carbons here, in the carbon-carbon double bond, this carbon is attached to one hydrogen, this carbon is attached to no hydrogen. So therefore, this hydrogen goes here, and the nucleophile, which is the bromine, goes to the other carbon. Okay, now having given you that, let us give you a few examples of electrophilic addition reaction. Once you know the Markovnikov, what we call Markovnikov rule, you can use that to determine the outcome of electrophilic addition reaction. You can use this rule right here, what we call the Markovnikov rule, to determine the outcome of electrophilic addition reaction. Okay, so let us give you a few examples. Okay. Okay. Now, ordinarily, what I will do, I will give you a set of reactions. Say, for example, take a look at this. There are three different ways in which I could ask you this question. I could either give you this starting material here, and I give you this hydrogen chloride, which we call the reagent, and then I tell you to give me the product. Okay? I tell you to give me the product. As you can see here, this reaction is following the Markovnikov rule. Hydrogen comes to this carbon here. It becomes a CH3 right here. And the chlorine goes to this carbon. And that is what you have here. So this is following Markovnikov rule. So we say this is a Markovnikov addition reaction. I could also give you the starting material. I could give you the starting material and give you the reagent, and I say give me this, and I'm sorry, I could give you the product and give you the reagent and say give me the starting material. These are the kind of questions I will give you in an exam. Okay? So that is two questions I could ask you just based on this reaction alone. Okay, the third question I could also ask you could be, I could give you the starting material, I could give you the product, and I say give me the reagent. Do you follow that? So those are three different ways in which I could ask you the same question. Okay, now let us look at the next set of reactions. This here, hydrogen bromide. What are we doing here? Adding hydrogen bromide across this carbon-carbon double bond. Okay? As you can see here, this carbon here contains one hydrogen, but this carbon here contains no hydrogen. So where does the hydrogen go? It goes to here. And that is why we have here. Okay, we have a CH2 here. It becomes a CH2. Okay? So you could use Markovnikov rule to determine the outcome or to determine the product of most of these reactions without actually knowing the reaction mechanism. Okay? Another example here, hydrogen bromide. By the way, this could be hydrogen chloride also. Could be hydrogen chloride. Okay, still following Markovnikov rule. Hydrogen goes here, right here, and the bromine goes here. And that's what you have here, your product. Okay, now, in this case, this last reaction here, this is a case in which we are adding water across the carbon-carbon double bond. So what are we adding here? We are adding the elements of water. That's what we are doing here. If you look at the product, because if you look at the next process, what are we doing here? If you take a look at this starting material, and you take a look at the product, you should be able to tell me, oh, what we've done here is to add OH and hydrogen across the carbon-carbon double bond. And to do that, we cannot do that with using water by itself. We use what we call a catalyst. This is an acid here. So, as we move on into chapter 8, this is going to be very important. Most of the reagents that we use, you need to know what those reagents do. In other words, if I give you water and sulfuric acid, you should be able to tell me what it does to a carbon-carbon double bond in your own language. Okay, right away, you should tell me water and acid catalyst. It could be sulfuric acid, it could be phosphoric acid, it could be nitric acid, any of the mineral acid. Sorry. or phosphoric acid or sulfuric acid. Any of these acid here we could use as a catalyst in order to add water across the carbon-carbon double bond. Or sometimes you may see or just do this. Use hydronium ion. What happens is, if you take water in the presence of any of these mineral acids, what do you get? You get this. You get hydronium ion, plus the conjugate base of sulfuric acid. Okay, this hydronium ion, think of it as this here. We are going to be using a lot of that in the future, this hydronium ion. Okay, anyway, so all of these follow Markovnikov addition. Okay, now before I leave this, notice that in the reaction mechanism that we gave you, we told you that the reaction mechanism goes through the formation of a carbocation as an intermediate carbocation. That is very important. So let us look at this. Now I want to say it is possible that those carbocations could rearrange carbocation rearrangement. Supposing I have this. Supposing I have that molecule. And I have this HCl, and I ask you, what is the product of this reaction? Anybody? Let me go ahead and number this. This is carbon 1. Let's say this is carbon 1, carbon 2, okay? Carbon 3, carbon 4. What is the product of this reaction? Where will the hydrogen go? Carbon 1? Very good. And therefore, you're going to form, based on the reaction mechanism, you are going to form a carbocation intermediate, because electrophilic addition reaction goes through the formation of a carbocation intermediate. Okay. If that is the case, this is the product you will expect to give me, right? Based on what we have discussed so far, you will say this is the product. Is that right? Okay, that would be correct based on what you know. But I would say this is not the product. Okay? Now what happens? If you go to the reaction mechanism, let us go to the mechanism for this reaction. HCl, the pi electron comes here, attach this to grab the proton, releasing the chlorine. You will still follow the Markovnikov addition, okay? We are going to form a carbocation on this carbon, okay? So now we get this. So far, so good. This is still following Markovnikov addition. But once you form the initial carbocation intermediate, what is going to happen? Anytime you form carbocation, if it is possible for the carbocation the molecule to rearrange to give you a more stable carbocation, that rearrangement will take place. And how does it happen? If you have an alkyl group or hydrogen next to that carbocation carbon, what is going to happen is what we call this here. This methyl group, what we call the alkyl shift, will shift, take the pair of electron with it. Okay? So we are going to get what we call an alkyl shift. And therefore we have this. Now the carbocation now will be on this carbon. So now we have this here. This is a secondary carbocation. Because it is possible for this alkyl to shift to this carbon here, we are now going to form a tertiary carbocation. And recall we told you the order of stability of carbocation. The tertiary carbocation is more stable than the secondary carbocation, and the secondary more stable than the primary. So this is what you get here. From your initial carbocation, you now get a tertiary carbocation. Of course, you know that this here, you see, have your chloride here. Keep in mind the chloride is still here. From here, so now the chloride now comes in, acting as a nucleophile. And then you get this here. Get that problem. So in an exam, what will I ask you to do? I will give you this starting material, I will give you this reagent, then I will give you this product, and I ask you to give me the mechanism of this reaction. In other words, show me exactly how this reaction occurs. That means you have to show all of the arrows, electron moving, and all that kind of stuff. Show the intermediate. Yes.
For the arrow from the secondary carbocation, why is there an arrow going from the C's?
No, it's not an arrow. We are moving these two electrons. See what is happening? You have this carbon-carbon bond. You are breaking it, okay. And you're moving those two electrons. The carbon is taking those two electrons with it and coming here, attaching itself to this carbon.
Is there any reason that happens?
Because it is going to form a more stable carbocation. Yeah. We know that. We could determine this using instrumentation. Okay, so for you may not know, but we already know that this actually happens in nature. Okay. I mean, when we get to spectroscopy, there are many instruments that we use to determine the outcome of these reactions. Okay. Okay. Supposing I have this. Supposing I, yes.
So for that question, how would we know that how would we know to move the carbon and not just go by the electrophilic addition.
No, because I will give you this as the starting material.
Oh, you'll tell us that.
I will give you the reagent. I will also give you the product. Okay. You see, no, I am not going to ask you. Give me the no. When we ask for medicine, everything will be given. Then what we'll be asking you, how does this happen? Okay. You follow that?
Yes.
Okay. Okay. Now let us see. Okay, that's a good question. Let us see how can we do this. Supposing we have this. I want you to do this with me now. Okay, supposing I have that, and I say I have this starting material, and I have this reagent, and I got this product. Okay, can you give me the mechanism of this reaction? Okay, what is the first step? Yes.
Move the carbon electrons to the...
Okay, we form the carbocation, right? The initial carbocation. Okay, very good. So what you do, okay, so this here, the pi electron will attack this in a mechanical fashion, right? Is that what you tell me? Okay, so now we form the initial carbocation intermediate. In a mechanical fashion, right? This hydrogen comes here. Then what happens? Plus the bromide here. What happens after that? This is the product I want you to explain. What happens? Exactly. Hydride shift. Okay? So this hydrogen here will shift with the pair of electrons. Now that's what we call hydride shift. Okay, so the hydride will shift, show the electron flow, and then we get this. Okay, and then what happens after that? The bromide comes in. Okay, here this is a secondary carbocation, and this is a tertiary carbocation. So now the bromide comes in, acting as a nucleophile, attacks this electrophile. At this point, carbocation is your electrophile, and that gives us this product here. Okay, before we leave chapter 7, let me give you one more problem on carbocation rearrangement. Okay, supposing I give you this. Okay. Okay. And I say I have this HCl, and I end up with this here, Okay, give me the mechanism for that reaction. You see the different ways in which we really could throw this question at you. But the basic is the basic concept that we gave you earlier. Okay? So what would be the mechanism for this reaction? Anybody want to try? The first thing you form a carbocation, right? Okay. Okay, so we have this. Okay? And the carbocation will be formed in a mechanical fashion, right? Okay, so this pi electron comes here, picks up this proton, we release the chlorine, right? And so we have this. When you have this kind of problem, you got to look very closely at the product and also take a look at your starting material. Ask yourself, what is really happening here? What is happening here? We are going from a 5-member cyclic ring system to a 6-member cyclic ring system. So apparently we must be getting some kind of ring expansion right here. Okay? So if that is the case, we have metal here, and we have this here. Because this hydrogen here is attaching to this carbon. Okay? Once it attaches to that carbon, this now forms a carbocation. That's the secondary carbocation. Then what do you think is going to happen? Then we number this. Let us say this is carbon 1, carbon 2, carbon 3, 4, 5, let's call this 6, let's call this 7. Okay? What is going to happen now? What do you think will happen in order to get this? We are going to get some kind of alkyl shift. It will be an alkyl shift. But what bond will break? Which bond will break? Bond between which carbons? Which one? One? No? No. Which bond will break? To expand the ring. We have to expand the ring. Which one? 1 and 5. In other words, if we break the bond between carbon 1 and 5, and we place this, we form the new bond between 1. Okay, by the way, let me say this is, let's call it 7, and let's call this 8. Okay. If we do this, we break this bond between carbon 1 and carbon 5, and then we place the bond, we form a new bond between 1 and 7. You see that? Between 1 and 7, what do you get? We get this. Trying to do this, okay? Okay. Okay. I will number the carbons for you to make it a little easier. Okay, let us number the carbon. This is C carbon 1, carbon 2, carbon 3, carbon 4. This is C carbon 5 right here. Okay. Now this is carbon 7, so that means we are, this is here, carbon 8 is here.
Why did you break that carbon?
Because we want to form a more stable carbocation. This molecule here wants to go from a secondary carbocation. Now we have right here a tertiary carbocation. So carbocations are very notorious for doing that. Anytime you form a carbocation, there is always a rearrangement if it is possible to form a more stable carbocation. Keep that in mind. Okay, anyway. So, what do we have here? We now have a tertiary carbocation. So we have here secondary carbocation. Now we form a tertiary carbocation. Now once we form that tertiary carbocation, don't forget we still have our chloride here somewhere. Now the chloride now will come here, acting as an electrophile. Let me use a long attack here, attack this carbon here. That's a long electron flow, 2 electron flow. And at the end up with this product here. Okay? So when it comes to carbocation rearrangement, the kind of question we will give you will be a mechanism question. In other words, give the mechanism of this reaction. We will give you the starting material, we will give you the reagent, we will give you the final product, and then you have to give the reaction mechanism. Yes? Which one? The secondary carbocation, just a minute. Which one? Which? Oh, this arrow. Oh. Okay, what we are breaking this bond, the bond between carbon 1 and carbon 5. And the 2 electrons, we are moving those 2 electrons to form a bond between this carbon number 7 and carbon number 1. So that arrow is going to carbon number 7. Okay. Also, sometimes, I'm sure you guys have seen this in your hour questions, we might give you a carbocation. We might give you a carbocation, say for example, if you have this. We tell you there is electrophilic addition reaction. To form this carbocation. Okay? And then we will not give you this starting material. In other words, we say, okay, there is some alkene that reacted with hydrogen bromide to form this intermediate carbocation. And then we tell you, give the structure of that starting alkene. Okay, so all you have to do now is say, wait a minute, if we have this carbocation here formed, and they are telling us there is a double bond somewhere, so either the double bond could be here, or the double bond could be here. So in some of those cases, you may have to come out with more than one possible answer. Because if I just give you this without giving you the starting material, this here, just as this compound here could give you this carbocation, right? This here could also give you the same carbocation. This could also give you the same carbocation. So in this case, you say, okay, you have a carbocation intermediate is formed, and give the starting alkene. In that case, it could be this here, or it could be this. So in your case, you have to give both of them. Okay, so at this point, we have come to the end of chapter 7, and now going to go to chapter 8. And I'm sure if you have noticed, we have just started organic chemistry. Okay, all of those things we did from chapters 1 to 5, those are just getting you ready for organic chemistry. Okay. Yes. Yeah, if the double bond was here, yeah, it would be the same as this compound. Yes. Okay. So now let us start with start our discussion of chapter 8. As you can see here, chapter 8 has a lot of reactions. And of course, chapter 8 also deals with the chemistry of alkenes, in which we will be discussing the synthesis of alkenes and reactions of alkenes, various reactions of alkenes. So what I want to do today, instead of starting with the synthesis of alkenes, I am going to go straight to the reactions of alkenes, and then we will come back to the synthesis of alkenes. The reason I want to do that, because we've already started the reactions of alkenes anyway. The electrophilic addition reaction, that is under the reactions of alkenes. Okay? So we are going to start reactions of alkenes. Of course, you know what this is. It's a list of concepts and topics that you should use to assist you in studying for the content of this chapter. Okay, I told you that we are going to go straight to reactions of alkenes. But before we do that, I want to show you another slide, just to impress on you the centrality of alkenes in organic chemistry. Alkenes are very important starting materials. A lot of the classes of compounds that you guys already know, we are going to be making them or synthesizing them starting with alkenes. For example, starting from an alkene, we could make an alkane, make alcohol. We've already shown you an example of that in the electrophilic addition reaction, in which we added water across the carbon-carbon double bond. That's an example of making an alcohol starting from an alkene. We make a halohydrin. Halohydrin are those compounds in which you have an OH group and an halogen attached to what we call adjacent carbon atoms that are next to each other. Okay, we could make 1,2-dihalide in which you have halogen attached to adjacent carbon atoms. We could make a halide. We've already done that. If you recall what we did in chapter 7, electrophilic addition reaction. Okay, those are halides that we were making. We will be making epoxide, cyclopropane. We will be making different types of carbonic compounds. We're making diols. Diols are those compounds in which you have OH group attached to adjacent carbon atom. Okay? Okay. Let us go back to... So now what we want to do now, we want to start the reactions of alkenes. But before we do that, let me give you a little bit of advice. In organic chemistry, there are two possible processes that we generally deal with. We look for, one, reaction product, or what I generally refer to as reaction outcomes. Then two, how do this reaction take place? That is reaction mechanism. How do this reaction take place? So what I'm going to do today, most of the reactions I will give you today will be simply showing you the reaction product. In other words, I will give you the starting material, I will give you the reagent, then I will give you the product. Later on, we'll come back and then give you the mechanism of some of those reactions. The reason I want to do that, over 80% of whatever questions you get in an exam is under this category, reaction product. Giving you the starting material, giving you the reagent, give me the product. Okay? Or give you the product, give you the reagent, give me the starting material. Those are the kind of questions that will come under category 1. Okay, so that is why I want to spend more time on that section. Then we'll come back to the actual mechanism. Okay? Okay. So make sure you get your pen ready. We are going to be flying now. Okay, reaction. Okay, reactions of alkenes. I will number them to make it easy for you. 1. Addition of halogen across the carbon-carbon double bond. Now, when we say halogen, we essentially just mean chlorine, or bromine. Those are the halogens that is of interest to us. So addition of halogens to carbon-carbon double bond. To form dihalide. To form dihalide. Okay. Example. If I have this, hydrogen here, hydrogen here, and I have, let us use bromine. This also applies to chlorine. Okay, bromine. I know some of you will be interested in the mechanism of this reaction, but I will give you that later. So what do you get? You get this product. You get a trans product. Of course, you have the hydrogen still here. And here, hydrogen here. Okay, so we get a trans addition product. So therefore, we say this bromine here, generally this bromine here, we generally use a solvent. In some cases, you might see a solvent called carbon tetrachloride. Okay, this here is just a solvent. A solvent is just a medium, just a liquid that allows you to mix the reactants so they will react efficiently. Okay, so if you see the carbon tetrachloride in there, do not be bothered by that. Okay, the reagent that is of interest to us here is bromine. Okay, but if you want to think of the reagent as being bromine in carbon tetrachloride solvent, that is fine also. So anyway, what does this reagent do? This reagent will add 2 bromine atoms across a carbon-carbon double bond such that the 2 bromine that are added will be trans to each other. Okay? So this will be a trans addition product. Therefore, I will refer to this reagent here as a trans addition reagent. I would say this is a trans addition reagent. Okay, now, if you take a look at this, in this particular instance, we are going to form two enantiomers. Because what are we doing here? We are adding bromine to here, another bromine to here. We are going to form two enantiomers. Which is to say that the product of this reaction will be a racemic mixture. You know what a racemic mixture simply implies? It will be optically, that the product of that reaction, the mixture itself will be optically inactive. So you ask, how do we know this happens? That's another way in which we can tell what kind of reaction is going on here. We could determine the optical activity of the system. So this reaction mixture will be, optically inactive. Even though the individual enantiomer will be optically active. Keep that in mind. Okay, anyway. So bromine or chlorine adding to a double bond, what you add the bromine or the chlorine across the carbon-carbon double bond in a trans addition fashion. Now, supposing we don't have it in a ring system. Supposing we don't have it in a ring system. Supposing this is what we have. Supposing we're starting with this cis-alkene. Supposing we're starting with that cis-alkene. And then we add chlorine. And we are chlorine. Okay? Let us be consistent. Say we have solvents in there. What is going to happen? This is still a trans addition reagent. So what are we going to get? We are going to get this. Imagine that chlorine is here. We have this carbon here. The other chlorine is trans to it. And now, what happens? One chlorine atom comes here. Look at this carbon-carbon double bond. One chlorine atom comes here. We are going to form this is an sp2 carbon. Okay, it's now going to become an sp3 carbon. So it pushes this down. Okay, the other chlorine comes from the bottom, pushes these two up. So what do we have? We have this. Look at this. This here, the ethyl group. Put down, and the hydrogen, of course, also put down, but coming towards you. Okay, here also pushes this up, so we have the methyl. And the hydrogen also push up, because now we are forming a tetrahedral carbon. We form this. Then you want to ask, how come the chlorine doesn't come from top and the other comes from the bottom? Yes, that happens. So if that happens, you're also going to get this. Okay, this pushes up, And this here, hydrogen is here, and this pushes down, and this is here. Let's call this compound A and compound B. Okay, when you go home, try this out. Both of these are enantiomers. Both of those are enantiomers. Now, that is starting with a cis isomer. Okay? If you check out the absolute configuration of this here, one of them will be SS, the other will be RR. I don't know which is which at this point. Okay? They will be enantiomers. Now, if you started with the trans alkene, okay, I will leave that to you. When you go home, try with the trans alkene and see what kind of isomers you get. Okay, anyway, now you begin to see we're beginning stereochemistry into the organic reactions. So what you see here, but the most important feature of this reaction is that this is a trans addition reaction. Trans addition reaction. What do we mean by that? This chlorine here, it is added trans to this other chlorine, and the same thing here. Okay. Okay, so that is reaction 1. You got that? Okay, reaction 2. Addition of hypoallose acid. Hypoallose acid is this here. Either chlorine or bromine attached to an OH group, or bromine attached to an OH group. This is what we refer to as hypoallose acid, this here. So if you take and we take an hypoallose acid, the problem here is to make the hypoallose acid, you need a mixture of bromine plus water. Okay? So we do not have, this is a very unstable species, the hypoallose acid. So to get the hypoallose acid, what we do, we use, in this case, bromine in water, or chlorine in water. But the net process, the outcome or the product will be that in which we are adding chlorine or bromine and OH across the carbon-carbon double bond. Okay, so let us see. The product will therefore be this. OH and bromine is a trans addition reaction. So this is also a trans addition product. And therefore, we refer to this reagent here as a trans addition reagent. In other words, anytime bromine water, we call it bromine water, or chlorine water reacts with a carbon-carbon double bond, what happens? the bromine and the OH will be added to the carbon-carbon double bond such that each one of them will be trans to each other. Okay? And the same thing will happen if you are dealing with a non-cyclic system. Okay, this is alkene. The same thing that happened with the addition of bromine or chlorine. If we take this chlorine water, let us use chlorine water. We will give you this mechanism later. Okay, what happens? We have chlorine coming from one side and then pushes the other group down, because now we are dealing with a tetrahedron carbon. And the hydrogen is here. And then this other, the OH, be anti to it, or trans to it. Okay? Okay. And you will also get the other isomer in which the OH is here and the chlorine is here. Okay? Those would be a mixture of enantiomers. In other words, you are going to form a racemic modification.
Is that true also for the enantiomer?
Yes. It's true for it. You get two enantiomers, yes. Yes. Okay, so now so far we're giving you two reactions, addition of bromine and addition of OH and chlorine, or OH and bromine. Three. Addition of water which is via mercuration, demercuration. To form alcohol. And this process we actually refer to as hydration. We refer to this process as hydration. In other words, we are adding water to the carbon-carbon double bond. Here, to do that, what reagent do we need? Say we take this, hydrogen is here. The reagent that you need, at this point you should begin to write down the list of reagents. This is what we call the mercury acetate.
Is that HG?
HG, yes, HG. Mercury acetate. Okay. Now this acetate here, this is the way we normally write it, OHC. So in the future, you see me just write OHC. That is acetate right here. Okay. So mercury acetate, step 1. In the presence of water, Okay, and sometimes we also use some kind of solvent. CHF, do not worry about it. This is just a solvent. Keep in mind, the solvent just allows us to mix the starting material in order to form a product. Okay, so no. It's water. You need water in there, but the CHF is just a solvent to make things mix together. Okay. Step 1, and then you follow that always. Step 2, sodium borohydride. Now this combination here, what does it do? It will add the elements of water across the carbon-carbon double bond in a mechanical fashion. Now what do I mean by that? So where do you think the water, the hydrogen will go? Where will it go, the hydrogen? So this is a mechanical addition. So keep in mind, this reagent here is what we call a mechanical reagent. Which one? Yes, both of them combined. You cannot separate them. Mechanical sodium borohydride is hydrogen, 4 hydrogen. Mechanical addition. Okay. Now, supposing you want to add water in an anti-mechanical fashion. Okay. Supposing you want to add water to form an alcohol in an anti-mechanical fashion, what reagent do we need? Okay, so I'll say that is, was that 4? Was that 3?
3.
Okay, so 4. Addition of water in an anti-mechanical fashion using hydroboration / oxidation. To give an alcohol. Okay, so use this same starting material again. Okay. So what do we get here? The reagent we use for that, we use borane, BH3, called it borane. And then after that, we follow that always hydrogen peroxide in hydroxide. Okay? So this reagent here, they work together as a unit. And what do you get? I want to be consistent. The last time I put the CA3 here, right? Let me be consistent. CA3. And I believe that was. And I said this was hydrogen. Okay. Okay. So what do we get? Anti-mechanical addition of water. So now the hydrogen comes here. The hydroxide goes here. Okay? Notice we say this is in other words, this is against Markovnikov. Markovnikov is the other direction. Okay, so this is anti-Markovnikov addition. Okay, what time is it? 5 minutes? Oh, God, madam. Oh. Well, let me give you guys a break. Okay, so when we come back, we're going to finish up on chapter 8. But I would advise that you watch the webcast that I posted in Blackboard for the lecture from last year. Yes. To do what? Oh, PD5? Oh, go back. Okay, so I will see you guys on Thursday. And when you come on Thursday, there will be a 10-minute quiz based on today's lecture. There will be a 10-minute quiz based on today's lecture. Okay. Yes.
I watched your old lecture before I came to class, and it took my notes. I have a question about